Okay, so we're talking about gravity here. And you've definitely lived on Earth for some period of time, and so you have experienced gravity. So when we talk about mass, mass has two properties. One of the properties, so we'll say two properties. And one of the properties is that mass resists acceleration, and we call this inertia. Another property of mass is that it attracts other mass. And so we can call this gravitational mass. And the cool thing is that we don't know why. We know how, meaning we can describe it in great detail, we can perform calculations, but we don't know why. And so there are theories about, well, mass distorts space-time and all that stuff. But anyway, it's interesting to think about. So when we talk about, well, how or to what degree does mass attract mass, we use Newton's law of universal gravitation. And so this is how we can calculate gravitational force. So the gravitational force between two masses, and so this is the mass of the two masses. In the case of you, excuse me, and Earth, one of the masses would be Earth, and so that would be very large. This is the distance between the two. It's tempting to just call that radius, but distance between two masses. Frequently, when we're talking about calculating gravity, we're talking about Earth attracting the Sun or Moon attracting the Earth, and so things are moving in circular paths, and so radius is kind of appropriate, but it doesn't have to be that way. Big G, this is universal gravitational constant. So you might want to write that there, universal gravitational constant, and it has a value of 6.67 times 10 to the negative 11. So this is, I'm just going to write this is a small number. I know that gravity feels like a big force, but compared with the electrostatic force, or electromagnetic force if you want to call it that, or the forces within the nucleus, it's actually very small. So this is probably intuitive. The more massive the objects are, the more they attract, and the farther away they are from one another, the less they attract. And in terms of the formula, the fact that masses are in the numerator means this sort of makes sense in terms of the formula, and the fact that r squared is in the denominator, this should make sense in terms of the formula. So the bigger r gets, the less F becomes. So make some approximations and calculate gravitational attraction between yourself and the person sitting closest to you. It's weird to think about gravity between two people, but that's the case. So here are you, and here's the person sitting next to you, and what's important is that when we're talking about the distance between two objects, we talk about the distance between the center of mass. So if I were to give you a high five, right, and there's a hand, that's a hand. Here's, okay. And so we're giving high fives. All right, the distance between us right here, we're actually touching. And so the distance between us would be 0. And if you look at the formula, if you were to plug 0 in there, you'd get an infinite force. And there's definitely not an infinite gravitational attraction when I give you a high five. So we talk about the distance between two objects being the distance between the centers of mass. And so a reasonable approximation for you and the person next to you, we'd have 6.67 times 10 to the negative 11. And mass is, I don't know, maybe you're 60 kilograms and the person next to you is 80 kilograms. And the distance between you would be something around a meter. And so we would plug it in like that, and we'd get a very small number for the force. So, yeah. Okay. excuse me. So when we talk about things in orbit, I'd like you to, so this is a thought experiment. And in this thought experiment, you can throw a baseball really fast from a really high tower. So there it is. It's this really high tower, and you wind up and you throw the baseball. And then you wind up and you're throwing it tangent to the circle, okay, perpendicular to, like, here's you, here's the line from you between Earth, and so you're throwing the ball perpendicular like this. So the faster that you throw it, so let's see, you throw it faster and it does this. And then you throw it even faster and it does this. And at some point, you throw the ball and it keeps falling. Well, okay, so we'll do that one. And then we'll zoom out a little bit. And you wind up and you throw it even faster than that. Here's the money shot, and it goes, falls. It's falling into the circular path, and it comes around and hits you in the head. So this is how things orbit, is they are falling towards Earth, but Earth is not flat. Shocker there, okay, Earth is not flat, and so what happens is the baseball wants to go in this direction, but it's pulled in that direction. And then at this instant, it wants to go in this direction, but it's being pulled in this direction. And at this instant, it wants to go tangent to the circle, but it's pulled in this direction. And so it doesn't actually take that path like that. It takes the circular path. But those are there just to illustrate the fact that this is the direction of the velocity in which it wants to go, and this is the direction in which it's being pulled, because it's constantly being pulled towards the center of Earth by the gravitational force. So that ends up being a centripetal force, pulls it into its circular path. So our satellites falling will definitely, if they weren't, they'd travel in a straight line and would not orbit Earth. They'd fly away. It'd be like that. But they stay the same distance away from Earth. They stay the same distance away. All right, and so what does weightlessness mean? So, excuse me, here is Joey the astronaut, and he's in his spaceship, and the engines are not going. And so Joey is in orbit around Earth, like that. It turns out that the mass doesn't matter. So you have a spaceship in orbit, and you have Joey in orbit, and they're both falling towards Earth, but they're falling at the same rate. And so weightlessness is kind of a misnomer or an oxymoron or something like that, where in order to be floating, quote unquote, in orbit, you actually need weight. So gravity does pull on you. If gravity didn't pull on you, you wouldn't have any weight and you'd go in this straight line like that. So gravity does pull on you or Joey the astronaut, but you are floating relative to, let's say, the spaceship that you're in. So gravity does pull on you, but you're floating relative to spaceship you are in. So you would experience something similar if you're in a really tall building and there's an elevator and you're up there and for some reason the cable snaps and you're falling and you and the elevator are falling, and so you would feel quote-unquote weightless in the elevator, and it would seem like you were just floating in this little room. And so the Vomit Comet, this video will be on the website, and so you should kind of take a look at it. But basically, this is the path that the plane takes, and so we have a big jet plane like this. And the idea is that the plane, the Vomit Comet, in this region is taking a parabolic path. And so it's just as if you threw something up, right? And it would take this path. And so the plane follows this path and you float inside, or the people float inside. So down here it experiences large acceleration. And then up here, people in the plane experience quote-unquote weightlessness. Weightlessness. So watch that video. All right. So the Cavendish experiment, this is something that I got to do in college. It was pretty cool. Cavendish was the first person to actually find the universal gravitational constant. And so when we look at this, GMM over r squared, and so Newton was able to say, well, I think that the gravitational force is proportional to the product of the masses and inversely proportional to the square of the distance between them. But he didn't know this because he didn't know how massive Earth was. And so Cavendish did this experiment where there's a torsional pendulum. So this is a string hanging from the ceiling. There's a little mass and a little mass. And this is a top view, so the string would be right here. And there's a slight attraction and a slight attraction. And so Cavendish using, well, when I did it, we had a little laser. Cavendish obviously didn't have a laser, but have a laser. So we bounced the laser off of a mirror and observed it on the wall on the side of an empty classroom. And so from the deflection there, we could determine the deflection here and then determine the force between this mass and this mass. So it was the first time when Cavendish did that somebody had actually been able to measure the force between two masses. And so from that, he was able to determine the universal gravitational constant, which we now know to be that. And what I love is that he called his experiment weighing the Earth, because you picture this, and it's like, hey, wait, how do we figure out how much Earth weighs? Okay, so lastly, the inverse square law. This is talking about gravitational force as a function of distance from the center of Earth. So the gravitational force that you could potentially experience is greatest when you're on the surface. The further away you go, the less the gravitational force is. So it's going to be proportional to the square of the radius. And we'll talk about that more in the next set of notes. And here, if you were to dig a hole in Earth, as you move in, as you move into Earth, so imagine this huge tunnel that goes all the way to Australia. As you get closer and closer and closer to the center, there's less and less mass inside pulling on you. So here's Earth, and here's you in this big tunnel, all right? And the only mass that's pulling on you to give you sort of a force towards the center is this. Everything out here is also pulling on you, but it sort of cancels out because some pulls this way, some pulls this way, some pulls this way, some pulls this way. So it turns out that only the mass in the sphere that is closer to the center actually pulls on you. So you can imagine something like, there are all kinds of practical reasons that we couldn't do this, but if we were to dig a tunnel all the way through Earth, and then you have this frictionless elevator type thing where you just kind of get in there and fall, you'd go really fast, and by the time you got to the center there'd be zero gravity, so you'd just be moving really fast and then but not accelerating, and then as you started to come out here, gravity would be pulling you back, and so you'd slow down and slow down and slow down and would end up on the other side of Earth. And it's kind of an interesting calculation to figure out how long that would take, which we can do when we talk about potential and kinetic energy. But it'd be a really easy way to travel across the planet for using very little fuel. Okay, thanks for listening.